Yesterday we were solving one kind of equation, and well, let me start. Before that, the learning goal we just took up, our understanding of the graph is part of how we solve the problem, right? So we do a bunch of algebra, we get some statement, but in order to find our answer, to interpret our answer, we have to look to the graph. I mean, there are other ways of doing it, but that's how we're doing it. Okay, we think about the graph. Today we're going to look a lot at graphs, but we're not going to use the graphs to solve. So it's very different, and I want to start with that because I don't want people to get confused or overthink the graphs. All the graphing and sketching that we do today all has to do with trying to just understand why what we're doing works. And that was kind of similar to what we did yesterday, but why we were talking about the cases of absolute values yesterday, right? Why what we're doing works. But you won't be sketching as a part of answering today's questions. Okay, a sketch doesn't become part of it. But we are going to look at graphs a lot. So if you feel like the graphing or the sketching that we're going to do goes too fast, or you're not really sure of the connection, don't worry about it too much. You have two responsibilities today. One is to learn how to do what it is we're going to do. And there are kind of steps that you can go through to do it. And then the other is, I suppose, to understand at a bit of a deeper level why it works. And I'm going to try to point out a couple of things that I just think are really cool, really neat connections, and it just helps us understand in a more broader sense of why thinking about graphs is important. I've talked a lot about that, but again, there's a neat little thing that will happen today about why thinking about graphs is important and how our algebra and our understanding of graphing really overlaps, and you can start to see it. But again, it's not really going to help you do what we're going to do. Okay, so don't let it confuse you. Keep those things separate. And then the other thing that you have to remember is yesterday, today, and tomorrow are all dealing with absolute values. Yesterday we noticed, you may not have noticed because we didn't have anything to compare it to, but we did a bit of sketching, and then we did something like absolute value of x minus 2 equals a constant. That's all we did, right? Equals 5 or something like that. And so that's one type of question, and that was one we were doing yesterday, and we had two cases, and then you had to interpret your solution after doing your two cases and kind of make sure you and get your answer, right? But that was when it's equal to a constant. So today, we're kind of doing two types of questions, although they're similar in some ways. But throughout these three days, you want to, in your head, I think, start thinking about this type I solve this way, this type I solve this way, this type I solve this way. I think that will help a lot of us to, when they all get mixed up together on a test, to be able to go forward. Because they're similar, but then different in important ways. And if you try to use one method on a different kind of question, I think you're going to start to confuse yourself. In some ways, they're all about looking at the cases, but because the questions are so different, we do it in slightly different ways. Okay, let's get into this. That's enough talking. And so we're just going to graph this just to, practice a little bit more sketching and graphing and remind ourselves about how, sure, this is a question right here that we are just going to solve algebraically, but there is a graphing component that's associated with it. So the left side of this equation, which is the absolute value of x minus 2, is like a question from grade 11. It's just a transformation. So I go to positive 2, right? That's my x-intercept. Your x-intercept is what value makes that thing 0. So I put in positive 2, minus 2 gives me 0. So that's my x-intercept. Okay, and I'm going to continue to try using my ruler here on my screen. And I go like that. And I go like that. Whoa. Okay. So this is the graph of y equals the absolute value of x minus 2. I hope everybody agrees with that. And then I'm going to graph the other one. I'm going to choose a different color. So 2x minus 1, I go down 1. And I go, my slope, remember we talked about this a bit yesterday, that graphing lines is actually something that we need to remember how to do. So I go up 2 over 1, up 2 over 1, up 2 over 1. There's my slope. Slope's a big deal. And I graph. Okay, and there you go. Where the two, so this one's y equals 2x minus 1. Where they meet is the solution. So I found the solution. It's not a point of intersection, like it's not an xy. If we're solving it, if we're solving this equation, the only part of that solution we care about is x, but that's the graphical representation of how you would solve this equation. Okay, so let's take a look at it. And how did we do this yesterday? We had to look at the two cases. So we're going to start with the negative case because we like the negatives to be on the left. It's a little bit easier. So here's my algebraic one off to the side here. When x minus 2 is less than 0, okay, and that means, let's see, when it's less than 0, I have to do this. Negative x minus 2 is equal to 2x minus 1. Right? That's from yesterday. It's not different from yesterday. It's that when that line, when it's negative, I'm actually using a different function. Right? So we make it negative and we do that. So that explanation came yesterday. So negative x plus 2 equals 2x minus 1. So let's see. I'm going to subtract 2x and I get negative 3x. And I'm going to subtract 2 from both sides and I get negative 3. And so x equals 1. Happy with that? Okay, and then our other case is when x minus 2 is greater than or equal to 0. I'm going to talk a little bit more about the greater than or equal to and less than or equal to today. It comes up a bit more interestingly in a different example, so we're going to talk about it. The easiest way to maybe think about it is just always make them all also equal to. So less than or equal to, greater than or equal to. It's a little bit of a form thing. Ultimately, when you interpret your final answer, that's where the importance comes in. But we also are trying to make sure we don't have inconsistencies throughout our solutions. That'll be more obvious when we do this later. Okay, so let's go ahead and do this. You can just solve it on your own. 2x minus 1. So I'm going to subtract 2x, and I get negative x. And I'm going to add 2, and I get 1. So x equals negative 1. Okay, so we're happy with that? Everybody feel good about it? Any questions before we move on? So we have two solutions, right? Anybody? Don't you notice something that's wrong with this? There's something seriously wrong here. What is it? Yeah. I didn't do that on purpose. That was a mistake. Why? Oh, you just thought I did that on purpose? What do you think? Does that matter? Yes, of course that matters. Look at, why do you think we graphed it? They cross in one place. We got two solutions. Like, this is one of the reasons why we graphed. There's a major problem here. I'm very sorry, I lied. I did leave that space on purpose. Very perceptive of you. So when x is greater than 2, when x is less than or equal to 2? Where's the problem here? How do we know which one's the right answer without graphing? If you look at the graph, you can figure out which one of these is right. Look at the graph. I'm gonna underline these because I like to split. It's almost like a title, but I just like it not to look like we're going from one line to the next. So put a line under where that goes. But take a look at the answers. Take a look at the graph. Based on that, which one is the correct answer? And then based on that, without graphing, because we're not graphing every time, algebraically, how can we figure out which one is the correct answer? What do you think? Say that again. X-intercept of this. We have this x-intercept. Well, you're on the right track, that's for sure. What do you think?
If you start off with the first one, so 11, and then see if
Okay, there you go. There's one way of doing it. You could sub your answers in and see which one works out. I encourage you to do that. And we're going to do that for another example down below, I think, if we have some time. But you certainly can always sub your values in and check them. But there's something else going on here. Another thing that when x is greater than 2, we do this version. But x is not greater than 2. This answer doesn't fit that domain. Why did that happen? Because when I extend this line down, it crosses again, right? But we don't want that one because that's this line, but it's this line in like theoretical land, not in actual absolute value land, I guess we could say. Does that make sense? So again, that's something I think that's worthwhile to think about. Remember what our cases come from. This should actually go down like that and they would cross there, right? So if I extended this graph, which is that, down further, it would cross, but that doesn't actually exist. That's why we have the cases, so we have to think about it. So I'm going to make a statement here. I'm going to kind of lightly cross that out so you can still see it, but we know that it's not a solution. I'm going to say not a solution. And I'm going to go, therefore, x equals 1, because this one's correct and the other one's not. So we have one solution, and I'm going to make a therefore statement to be that much more clear about which ones are good and which ones are not. But every time we get one that's not, we're going to say that it's not. If it's not a solution, we're going to say that somehow. And then the ones that are a solution are left, but then we're going to summarize. Any questions? Yes?
What if you didn't graph it? How would you know?
I would look at this answer and ask myself if it's in that range. Is this x solution down here, is it greater than 2? It's not. It's less than. Okay? So this is part of what's different today from yesterday. Yesterday you didn't have to do that because it was a straight line. Once that line tilts, okay, it's going to hit sometimes, but it's not going to hit, but it might hit the other imaginary branch if we extended it. Like all kinds of things can happen. And then the other type of question that we're going to do today is similar, where you might get algebraic answers that aren't actual answers. So we have to think about our cases and interpret our solution. We get all kinds of different things coming. A lot of today is about how we interpret our solutions, where the visual comes in a little bit better. Does that make sense? Okay, so, or you could check. Like you could also do a check, or you could do a bit of both. Just check in your head, just check on your calculator, do a quick check. If you're not quite sure, that will always work too. All right, so let's just try another example here. Okay, so our first case is going to be when 4 minus x is less than or equal to 0. So I'll move the 4 over and I get negative. You don't have to do this in steps, obviously. And then I get x greater than or equal to 4. These ones are a little wonky because when you divide by the negative, it flips the sign and you thought you were like below, but now you're kind of above. Okay. But this still started, here's something that a mistake people make. This still started as a case where the absolute value was less than 0. Doesn't matter what x ends up being. What matters is what the absolute value is. So this is still the case where we do negative of this. Okay, and go ahead and solve that. Yep. For now, I would just put it. When in doubt, for all of these, you can just put it. Everybody get x equals negative 2? And then what do we do? Our restriction was x has to be greater than 4. It's not greater than 4. So that is not a solution. Okay, so then our other one, when 4 minus x is greater than or equal to 0. And so I do the same thing. And so this is a case where we don't have to add the negative. So add x to both sides. And I get x equals 1. 1 is less than or equal to 4. So this one's fine. So therefore, x equals 1. Could you have a case where both of them don't work? Like you could have an absolute value and a line that never cross. So yes, see how again our understanding visualizing different graphs can help us make sense of different situations. And in fact, if I was really good at graphing, I could even kind of visualize some of the cases where that might happen. If we get to it at the very end, we've only got 30 minutes left. We're going to get to an example that will hopefully show some of that. Okay, I'm going to very quickly do a left side, right side check. Okay, I'm doing it kind of informally because, like I said, I want to do it quickly. So I'll do them both over here. So for the one on the left, I get the left side equals the absolute value of 4 minus negative 2, which is plus 2, which is 6. And the right side is 3 times negative 2, which is negative 6. So it didn't work out, right? Which we expected because that was not a solution. And then this one, I get left side equals the absolute value of 4 minus 1, which is 3, right? 4 minus 1 is 3, absolute value is 3. And the right side, I get 3 times 1, which is also 3. So it does work in that case. So the check will work out. The check sometimes, I don't know, gives you a little bit of extra like faith or like convinces you as to why you get these answers algebraically, but then they don't actually work out in the case of absolute values. It's a bit strange. Different stuff, for sure. Mm-hmm.
How would it work if you were to get infinite numbers, which is like basically the same way?
We're going to see that. And it will look, it will look like it looked in grade 10. Do you remember doing linear systems? when you do linear systems, you get 3 different possible answers. If they're parallel lines and they never cross, something wonky happens in the algebra. If you just get an answer, or if it turns out they're the same line, they just were written differently, again, something wonky happens in the algebra. So that's the same here. And all those cases can happen here, sort of, and more, and it's kind of complicated. All right. Any other questions? So that's 2 examples of when an absolute value equals a line, different from yesterday. And you got to think about if your answer is a viable answer. And those are the only 2 examples of that kind we're doing today. There's obviously practice. I'll say now this is not on the quiz. None of this is on the quiz on Friday. And so over like tonight and tomorrow, if you're making sure that you're ready for the quiz, then the rest of the day, Friday, we're not doing anything new. It'll be like a work period where you can maybe catch up on some of this work or ask questions, that kind of thing. So there will be extra time to go over this because I realize it's a lot. Okay. So this one is the other type that we're doing today where we have 2 absolute values. Okay, 2 separate absolute values in the same question. Whether they are on the same side of the equal sign or different sides doesn't matter. Either way, if you have 2 absolute values, this is the technique we're going to use. We're going to show you the graph quickly, and the only point, so go back to the question. If we look at the question again, x plus 2 is going to be the orange one because I've gone to the right or to the left 2, and x minus 3 is going to be the purple one because I've gone to the right by 3. Does that make sense? So those are those 2 graphs. It is not the graph of the whole left side. It's not the graph of all of this. This is the individual graphs of those. And this is where I'm not going to spend a ton of time on this. So if it doesn't quite click with you, don't worry too much about it. It's not going to help us solve, but it's a quick explanation for why the strategy we're going to use to solve, why it's what we have to do. Okay? To the left of -2, I'm using the negative branch of both functions. Right? Let's see if I can demonstrate that. So starting from here, right around there, I'm using the left branch of both. Okay? Between those 2 red lines, I'm using the left branch of the purple. Remember how we talked yesterday about cases? An absolute value is actually made up part of one straight line, part of a different straight line. And you put them together and you get your absolute value function. Remember talking about that? So that's what I'm talking about right now. So I'm using the left arm of the purple one and the right arm of the orange. And then to the right of the red line, I'm using the right arm of both. So what do I have to consider when I solve this question? I've got to look at all 3 cases. I've got to look when they're both negative, when one's negative and the other's positive, and it's a particular one, and when they're both positive. Don't just pick a random one that's negative or positive. You've got to get the right one. So we're going to look at all 3 cases. Okay, and this is why. And if you had more absolute values, then it would all of a sudden you'd have a whole bunch of different cases, but we're not going to do that. Okay? Okay, so I hope that makes sense. If it doesn't, then I would strongly encourage you to think more about it. But ultimately, you have to know the process that we're about to do here. So here's what I'm going to do. I am going to write the x plus 2 and the x minus 3 over here on the left. I'm going to do a number line. My number line's kind of below. It doesn't have to take up the whole page, but I'm going to make it nice and long for now. You do have to be clear. Like if you choose to slightly change how you do this compared to how I'm doing it, you got to be clear. So when we do a learning goal on this, if I'm circling things and saying things are missing, that's my feedback to you that something's wrong. In fact, that reminds me on the learning goal that I handed back today, There was a couple of cases where I circled things, and sometimes I wonder if I circle something in that green pen, people go, oh, that's probably not a big deal. No, that's a big deal. Like if I'm circling something, you're probably going to lose marks on that on a quiz or a test. That's me trying to tell you this is not acceptable. Okay? So keep the, or if I say form or something like that, that means losing marks kind of form. If it's not that big a deal, then I probably leave it alone. Or I might write be careful or something like that. Okay? Then here's what I'm going to do. I'm going to write my two x-intercepts, because again, going back to the graph, the x-intercepts are where these things occurred, right? That's where it changes from one branch to the other. Below -2, I have to make both of them negative. Okay? Right? Because I got to make sure I'm using the right branch of both of them. Above +3, both of them are positive. Between them, as I said, one of them has to be positive and one of them has to be negative, and it's not random which one's which. Well, when I cross to -2, the x plus 2 is the one that becomes positive, and the x minus 3 doesn't become positive until I cross 3. You could plug numbers in to think about it. If I put 0 in, okay, one of these is positive and one of them's negative. The one that's negative, I take the absolute value of that, which is like by doing the negative of it to make it positive again. I hope that is clear. So here's our 3 cases. And now I'm going to just start solving them, but I'm going to sort of retitle my cases for clarity. So this is important to do. You have to do this. This one is when x is less than or equal to -2. And in this case, both are negative. If you want to just watch what I'm going to do. I'm going to rewrite my equation, but without the absolute values. And I'm going to go, so negative x plus 2 minus x minus 3. So see how I've made them both negative? And then I'm going to solve. So negative x minus 2 minus x plus 3 equals 15. Negative x minus x is negative 2x. 3 minus 2 is 1. So when I move that 1 to the other side by subtracting, I get 14 and I get x equals -7. Is -7 less than -2? So this answer is good. I'm going to just make a check to make a mental note to myself that this is good. This next one is, it even looks like it. It's between the values of -2 and 3. So -2 less than or equal to x less than or equal to 3. Right? In this interval, in this section, the x plus 2 is positive, so I'm just going to leave it alone. The x minus 3 is negative. And now I just solve. So x plus 2 minus x plus 3 equals 15. X minus x is 0x. Subtract 5 from both sides, I get 10. Does 0x equal 10? Divide both sides by 0 and x equals 0. I could see some people trying to do that. Whoa, oh my gosh, no. This is a problem. 0 times x is 0. So this is like 0 equals 10. This is never true. Therefore, no solution here. See how we're like stating it. So this one's no good. And it wasn't like no good because I got an answer that wasn't in the domain. It was no good because like the algebra was nonsensical in the end. But we know that from grade 10. That's what we talked about briefly before. From grade 10, we've kind of seen this happen. We're going to look at a different visual of this very quickly because we are kind of almost running out of time. But I don't know, all these visuals are really interesting. Okay, let's do the next one. So this is when x is greater than or equal to 3, okay? And both of them are positive. So I just basically write this x plus 2 plus x minus 3 equals 15. And I get 2x equals 16, x equals 8. That one is also fine. Okay? And so I've got two answers that are fine. Therefore, x equals -7 and x equals 8 are my two answers. This is the doing of today. Like there was like that other example that we did two examples of just that was one type, but it's a little bit easier. This is the big one. Break it into 3 cases. Sort of determining which cases. This is the little strategy we use to determine the cases, and then we make sure we're clear about which case we're in. Come up with all of ours. Look at the answers and interpret the answers, deciding which ones are good, which ones are not. And we're going to get all kinds of different interpretations, all kinds of different answers. If we get through all the examples, you'll see them. Here's the graph quickly before we move on to the next one. So that was the two graphs individually. This is actually the left side of the graph. So this is what x plus 2 plus x minus 3, what that graph actually looks like. And again, if you like this stuff at all or have any interest in math or anything like this, I would encourage you to spend some time looking at this, like open up GeoGebra and take a look at these things. But any time you graph the sum or the difference of two absolute values, you get this funky thing in the middle. But there's well, not any time. There's a kind of a special case. If one of them was 2x, then that wouldn't happen. But if it's x and x, but there's a reason why. And if you think about the relationships, you can see why. It's interesting. Anyway, so that's why we had two answers. And that's why the middle one didn't work out, because this line is parallel to that line, right? Like it actually kind of makes sense that middle one gave us some nonsense. But you don't need to know that this is what this graph looks like. You're not going to have to graph. But it turns out that's what it looks like. So I've got two answers. One of them was that when x equals 8, and one of them was when x equals -7. There you go. You can see them on the graph. Okay? Any questions? Now we're just going to roll through as many examples as we can get through. Any we don't finish today, we'll finish probably Friday, actually. The rest of the examples are just more practice, and then also interpreting some different kinds of solutions. But I suppose at this point, you could do all the algebra for all the questions in the homework, but then the solutions, some of them might seem strange to you, so you couldn't interpret them until we maybe talk about it. Although it would be great for you to think about it on your own, but it can be harder. So we've got two. So see how this one, the absolute value signs are on different sides of the equal sign. So this one's different. So I've got 2x plus 1, and I've got x minus 4. Number line, okay, -1/2 and +4 are the two x-intercepts. Here they're both negative, here they're both positive. Between them, 2x plus 1 is that x-intercept. So when it crosses that x-intercept, it becomes positive. Or again, you could throw 0 at it and notice that you get a positive answer. Throw 0 at x minus 4, it's still negative. Right? So you gotta think about which one's positive and which one's negative. So this one to the left, they're both negative. Make sure you have brackets around. It's right. The whole thing becomes negative. So I get -2x minus 1 equals -x plus 4. -x equals 5, x equals -5. And that one's good. Oh, I forgot to title this, sorry. X is less than or equal to -1/2. That's that one. You can't just do it under this part of the number line. I know that seems like what we want to do, and in my head sometimes that's kind of how I visualize it. But don't do that. Write the title, because it's just going to make it that much more clear when your work's being looked at by somebody else. I hope I'm not going too fast. Stop me if you have questions. But a lot of this is going to be just working with it and practicing and going through it and thinking about it. But, you know, if you're confused as to why you do something, you've got two options. Ask, we talk about it, we visualize, we think about it, or just memorize what you do. I don't usually encourage the memorizing thing, because eventually that's going to catch up with you. But sometimes to get you through a hump, you memorize, and then as you work with it, things start to click. Like there are different ways of doing these things, right? So negative 1/2 less than or equal to x less than or equal to 4. One of them is negative, one of them is not. So I've got 2x plus 1. 2x plus 1 equals negative x minus 4. 2x plus 1 equals negative x plus 4. Move the x over, I get 3x. Move the 1 over, I get 3x equals 1. Is 1 between negative 1/2 and 4? Yes. That answer is still fine. Nothing wrong with that one. Last one, x greater than or equal to 4. Both positive. 2x plus 1 equals x minus 4. Move the x over, I get x. Move the negative 1 or the 1 over, I get negative 5. Oh, that one is not. Because negative 5 is not greater than or equal to 4. Not a solution. So this question had two answers. Very quickly. There you go. That's like it's got two answers. And I can tell visually that it's never going to cross again. Like when I'm visualizing these two different absolute values, one of them is steeper because it's the 2x. Right? So it crosses twice, but it's not going to cross again. Again, I don't know that that's going to help you do it, but it is eventually important for our understanding to visualize these things. Any questions? Okay, let's keep going. If you want to start this one on, like, folks, I know that this is how people feel in math class sometimes. Is they're overwhelmed. They're like, you just start, like, that voice inside your head, I can't do this, I can't do this, I can't do this. It's too hard. Break it down into steps. The first step is just taking the absolute values and writing them off to the left. Like, that is something everybody can do. This is what I mean by the process itself, whether you memorize it or whatever. That's not hard. Okay? Drawing a number line is not hard. 2x minus 2, what's the value there? Move the 2 over, becomes positive, divide by 2. If you get this part wrong, folks, the whole question falls apart. You're going to get maybe 0 marks on the question out of a lot. Some of these are going to be worth a lot. So you got to get this part right. So this is positive 1, and the other one is pretty obvious. It's positive 3. Both negative. When I cross the 1, that's where the 2x minus 2 came from. So that one becomes positive. The other one's still negative, and over here they're both positive. Unless you draw your number line in a weird way, that's how it should be. Again, that's why it helps to have consistency of drawing number lines from left to right, negative to positive. As long as you draw it negative to positive, then yes. Yeah. But you got to get the 1 on the right side. If you put the 1 over here and the 3 over there, you've drawn your number line backwards, and you're going to really confuse yourself. So you got to get the numbers in the right order. Okay, so this one is x less than or equal to 1. So they're both negative here. Negative x minus 3 equals negative 2x minus 2 minus 4. All right, what are we doing here? So I'm adding 2x, I get x. I've got negative 2, and I'm subtracting 3 more, I get negative 5. That one looks fine to me. Agree? Okay, here, 1 less than or equal to x less than or equal to 3. Which one's negative? The x minus 3 is still negative. Negative x plus 3 equals 2x minus 6. Subtract 2x, I get negative 3x. Subtract 3, I get negative 9. Divide both sides by negative 3, I get x equals 3. Again, even a small mistake like missing the negative sign is going to give you a totally different answer, and then your interpretation is going to be way off. Because if I got x equals negative 3, that's very different from x equals 3 when we're talking about an interval where it may or may not exist. I'm going to quickly do the other one. X minus, whoops, this is where x is greater than 3. 2x minus 2 minus 4. So I get x minus 3 equals 2x minus 6. So now I'm going to subtract 2 from both sides. 2x, I mean, and I get negative x. And add 3 to both sides, I get negative 3, and I get x equals 3. Look what happened. What happened?
You got the same solution twice because it was right on the line.
It's right on a very, very good. If you're visualizing what I think you're visualizing, that's fantastic. It's right. Let's take a look at what this looks like. Again, you don't need to know that the graph looks like this, right? But it might help some of us. Here's question. Look what it went right through. So it hit both the positive arm and the negative arm. And so how should our less than or greater than signs look? It doesn't really matter. This answer fits both of these. Less than or equal to this, greater than or equal to, oh, I missed the equal to, of course. You have to have an equal sign on at least one of them. Because if I had an equal sign on neither, technically that wouldn't be an acceptable answer. Which is wrong, because it is an acceptable answer. It is an answer. If you have it on both, I mean, it's just the same answer twice. That's fine. I don't write it twice. I don't say like it's the same answer twice. We're just going to say, therefore, x equals negative 5 and 3. See how it always helps to kind of rewrite so to really interpret and say, okay? So again, this is something where I know some teachers would say like, no, you're not supposed to write it twice. You have to pick one. I'm not worried about that, okay? Because it's not wrong. Nothing you've done here is wrong. It's true that it hit through the negative of this, and it's true that it hit through the negative of that, because that's where those two arms meet anyway. So this is all good. But you do need to have, so I would just, here's my answer to your question from before, right? Put equal signs on everything, and then you're safe. But you got to have an equal sign on at least one. So one of these two and one of these two. And as long as you do that, you're going to be okay. You have your hand up?
Yeah, I think it was the same question that was asked before.
Yeah.
Just like, is it ever wrong to put an equal sign, like on the greater than or less than?
Not in these cases.
Yeah, yesterday it wasn't on the less than.
So because we don't necessarily need it,
Okay.
but it's not wrong to put it.
Okay.
Because those two lines meet there. But there are other kinds of graphs that we're not going to look at today, we're not going to look at in this unit really, that don't meet. And then it would be wrong. So it's not like it's never wrong. In some cases you need to consider that. but in absolute values in these questions, we don't. We're gonna try to squeeze in one more here. We've got 5 minutes left. Yeah, this is a good one. If we see this one, I have a few more examples, but I think we'll be okay. Again, go ahead and get started. If you want, just try the first step. Try to do your number line. Okay, so on the side where they're both negative, okay, less than -2. Notice what I did here. This one was subtracting this. So I changed it to plus because 2 negatives make a positive. However you choose to do that part, you go ahead and do it. Whatever makes most sense to you. Like some of us have a lot more practice doing, these kind of linear equations. You can do a lot in our head. So I know I go through this a little bit quickly sometimes. But with a bit of practice, this part shouldn't be the hard part. Okay, so whatever it takes though for you to think through that, don't let that be the mistake that you make in all of this process. Oh my goodness, right? Again, with the same kind of thing that we saw before, 0x equals 6 is not true, so there's no solution here. Continuing on. We've only got a couple of minutes, so I'm going to whip through because it's the interpretation that's important. We're not going to quite get to it. So let's see. I've got 1 here. I'm going to subtract 1 from both sides. I get 2, and I get x equals 1. I'm going to leave that answer for a minute and do the next one. X is greater than or equal to 1 is this one. And so that's where they're both positive. So I get x plus 2 minus x minus 1, right? That negative is still around those brackets. So I get x plus 2 minus x plus 1 equals 3. So I get 0x plus 3 equals 3. 3 equals 3. Aha! What happened? This is always true. So this whole interval is a solution. And take a look. This was the end point of that interval. So it's included in my solution. This part was not true. So we'll talk about this again. Don't worry. I know that this is too bad that we're doing it at the very last minute. My solution to this problem is actually that. My solution to that absolute value equation at the top is it's always true when x is greater than or equal to 1. It was true when it's equal to 1 here, and it was true for every value here. Watch the visualization. So that's what it would look like algebraically. That's how you interpret. Don't pack up. You need to watch this. This is really important. No. That's the graph of the left side of the equation. why is that the graph we're going to look at it? Because it's really interesting. We're not going to get to today. But look, starting at x equals 1, this graph equals 3. So there you go. Okay? Starting there, it equals 3, but everywhere else, it didn't equal 3. So that's the visual of it. And I guess I'm going to leave the rest of this because I'm not going to try to squeeze it in bells about to ring. Practice the algebra. Okay, we're going to do more. The stuff we do tomorrow is a little bit similar. The interpretation can be a little bit different. We'll take a look at some of these other examples. But practice the algebra, and we've got a bunch of days for the interpreting of solutions to really come together.